here as well, record on this computer. I'll also show captions in English. Okay. There we go. So, all right. So, I'm showing the D2L homepage. I forgot to put a week 2 announcement up before class, so I'll get you guys a week 2 announcement that's going to have the week 2 schedule. Okay. Let's review what you can do if I forgot to post the week 2 schedule and assignments. What you can do is go to the syllabus. Well, one thing you can do is you can remind me if you want. Feel free to shoot me an email or a text and say, hey, can you post a week 2 announcement or a week 3 announcement or whatever? But the other thing you can do is just take a look here at the schedule in the syllabus. I'm trying to highlight this. I can't really highlight it. That's okay. Right there. There's week 2. So you see Monday, MLKJ Day, no class. Here's Tuesday. Today we're going to talk about section 2.3, a little bit of 2.4 as well, actually. But we've got an activity and a couple more sections, and then you've got your exercise set 2, which we do on. Oh, thank you. Oh, I did. Yeah. Exercise set 2, which will be due on Friday. Okay. Speaking of exercise set 2, you go into the if you go into assessments, exercises, I have put that exercise set up right here. Exercise set 2 is right there. So you can open that up and look at it. When you look at it, well, I'll show you what it looks like. Again, when you open exercise set 2, it gives you an option to submit your assignment, which add your file right here, right? But then also, it's got the actual PDF attached. So there it is. I'll try to get this printed for you guys before class tomorrow, so that when I see you on campus, I can hand you a copy of this paper assignment for you to do before Friday. So some of what's on here is stuff we've already done, right? So this is like evaluating this limit numerically. So you can use a calculator. So I've given you a little table of values, 1, 2, 3, 4, 5, 6. So, you can choose exactly what values to pick, but I want you to do 6 of them. Okay, this is a 2-sided limit, so don't forget to do numbers on both the left side and the right side, and you're looking for a trend towards something.
So you could just put like 1, 2, 3, 4, 5, 6, and that will count as.
No, you can't just do anything. You do get to pick, but you can't do anything. Does that make sense?
Okay.
Because what does it have to do? It has to be, this is the limit as x approaches 0. Do you see that right there? It's a little small. Let me zoom in. Limit as x approaches 0 right here. So you got to pick numbers that are getting closer to 0.
Like 1 and 2 and -1 and -2, like those numbers? Or
You're picking integers, but you got to get away from integers, because integers are not going to be useful to you at all here. You got to pick numbers really close to 0. So like 0.1. Yeah, stuff like that. Or 0.0001, like really close to 0, getting closer and closer. And you pick a few numbers getting closer. So you see it. So you want to be able to see not just one number, but you want to be able to see a trend, like a trend towards something. So just like we did in class in the activity. You got your notes. There's also some examples in the textbook that show how to do this, and they do it very similar. So you can take a look at that. The second one here is similar to what we did in class as well. So here you're figuring out, actually this is the one I showed you guys, because you asked what it would look like on a test or a quiz, and this is what it looks like. So this is the one I showed you. So you got that. And then the rest of this stuff, I'm going to teach you a little more about this sort of thing over the next couple of days. So I wanted to show you that is there and ready for you. Now, okay. So there is There was also a request to go over how to do homework quizzes again. So let's go back in there. I'm just going back to the home page here. Homework quizzes are another thing you can find here on this assessments drop-down menu. Homework quizzes. A homework quiz is really not a quiz at all. That's why I put it in quotes. Because while we are using the quiz function here on D2L, it is actually just a mechanism for you to report your own homework completion grade and put it in the grade book yourself, instead of me having to do those things. So let's look at how you do that. Chapter 2, homework. You open that up. You say you want to start the quiz. I guess I can't start it, but I'll let me do something to make it so that I can start it. Go back to my regular instructor view.
I have a question.
Go for it.
Is there a limit button on the calculator?
No.
Is there there's no limit button on the calculator?
No. Calculators are not programmed to do limits. Limits are too nuanced for calculators. Well, actually, that's not true. That's not true. It depends on the type of calculator. If you have like a TI-84 or below, then it can't do it. But I guess some of the more complicated ones that have a CAS, have you heard of CAS? That's like computer algebra system. Those ones might be able to do limits, but you're not allowed to use those functions. So you can't use a CAS calculator to do limits and derivatives and things in this class. It's not allowed. You got to do it the way I show you to do it. You got to do it by hand. What was I doing here? Oh, I was going to preview it. That's what I was going to do. Yeah. So you click Start Quiz, and then it looks like this. And if you've completed, say, 70% of the homework, you click true, true, true. It's kind of annoying, but you got to do them all. True, 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 true. Make sure you click all of them, because if you just click true on number 7, then you won't get the points for the first 6. That's how it works. They're just 1 point each, so you're just giving yourself 7 points. And I guess technically it doesn't matter which 7 of the 10 you check. So you could pick any 7 of them. But I think it makes most, don't do it don't do that. Just pick the first 7, because that'll keep things nice and organized. And then either you can leave these ones blank, or you can click false on these ones. All right, and then submit quiz. We've left 3 unanswered. That's fine. We submit the quiz anyway. And then it says my score is 70%, which is exactly what I wanted it to be, because I completed 70% of the homework, right? In this imagined scenario. This is a self-reported grade, so you're on the honor system, right? Just report your completion. So you can do this at any time, and you can retake this quiz as many times as you want. So that means that at any time in the future, you can complete more of the homework and then submit an updated percentage score. They're all in increments of 10%, so it's round to the nearest 10%. Questions about that? Okay. 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 Cool. Well, let's go ahead and move on to our next topic. Let's start the lesson. The lesson proper. Screen. Gotta get the chat open, as well as a few other things. That, and that. Okay. All right. We are. So today, we're going to do a little bit of section 2.4 today. We're actually going to start with something from 2.4. To be honest, I kind of think that 2.3 and 2.4 are in the wrong order, in my opinion. 2.4 sort of deserves to be first, but whatever, it's okay. Let's review the idea of continuity. Okay, this is what continuity looks like, or like maybe even like, whatever. That's what continuity looks like. Continuity of a function can be described informally by saying that you can draw the graph of that function without lifting your pencil or pen off of the paper. It's a continuous graph that connects.
Wait,
Okay.
wait, say that again. Continuity is writing the line.
Informally, so this is not the strict definition, but informally, it's defined as you could describe it by saying that you can draw like a function is continuous if you can draw its graph without lifting your pen from the paper. Okay, informally. But a formal definition for it involves the concept of a limit. And it's this. A function, which we'll call f of x, is continuous at some specific x value, which we'll call x equals a, if three things. One, f of a exists. Two, limit as x approaches a of f of x also exists. And three, those two things are equal to each other. Which is kind of the main point, but I guess you need the first two in order to get the third one. So I introduced this concept last week when we were looking at the graph, right, and going through like how to figure out how, like, kind of talking about the difference between the function's output value versus like the value of the limit, right, which would be what you're getting close to. And if those two things are the same equal to each other, that's continuity, right? So then you can say that, like, if a function is continuous on its entire domain, that just means it's continuous at every single point in its domain. But this is the definition of continuity at a point. And this could happen everywhere. And then you have a continuous graph. I just wanted to introduce this definition. We're going to go through and talk about this in a little more detail. We're gonna kind of run with this idea and talk about what are like different types of what are called discontinuities later. But for now, just remember that let's do a little quick examples of discontinuities. Over here, something like a jump is an example of a discontinuity. Or like a hole is a discontinuity, or a vertical asymptote can also be an example of a discontinuity. So those are examples of discontinuities, things like that. Okay. All right. So the reason I introduced this is because when it comes to evaluating limits, if you know that a function is continuous, you can just figure out what the limit is by just plugging the number that x is approaching into the function and evaluating the output. So zooming in on this right here, if we know that a function is continuous, we can evaluate this limit by just evaluating this f of a, right? Basically evaluate the limit by just plugging the number into the function and get the output. If you know it's continuous, those things are equal to each other, so you can, it's that simple. All right, so it's really useful to know when a function is continuous and when it's not. So we're going to establish a couple of theorems, which I'm not really going to prove to you, but we're going to take them for granted. A theorem is like a fact in math that can be proven. And a theorem is often accompanied by a proof. We're just going to present the theorem and then use it. Okay. So the first theorem, okay, so this isn't, I'm not going to word this exactly like it's worded in the textbook. I'm going to kind of combine a couple of things together here. Algebraic functions like polynomials, for example, power functions. Let me put that first, actually. So I like to put power functions before polynomials. Power functions, polynomials, rational functions, radical functions, etc. Okay. Those sorts of functions are continuous wherever they are defined. Algebraic functions like power functions, polynomials, rational functions, radical functions, etc., which is a lot of the types of functions that you study in college algebra. Okay, not all of them. There's a couple things I've missed. I haven't included yet, but we'll get to those in a second. These are all continuous wherever they are defined. So, example, the square root of x to the power -5. 2x cubed minus 7x plus 8. X plus 2 over 1 minus the square root of 7x. I mean, etc. Right? Dot, dot, dot. These are the types of functions that are called algebraic functions. These functions are continuous wherever they are defined. An example of using that fact would be like to say, well, okay, the limit as x approaches 2 of x cubed minus 3x plus 5, this is a polynomial function. Is it defined when x equals 2? Think about that for a second. Can you plug in 2 to this function and get a valid output?
Yeah.
You sure can. And so that means that this function is continuous at 2, and therefore we can evaluate this limit by what is called direct substitution. 2 cubed minus 3 times 2 plus 5, which is 8 minus 6 plus 5, which is 7, I think. I usually do like a square. So this right here is called direct substitution. Any questions so far? This is a very powerful theorem because it means that for most situations with familiar types of functions that you studied in college algebra, if you're asked what the limit is, you can just plug it in. That doesn't mean that's going to be true on most problems, because we're going to spend a lot more time and energy focused on the more challenging situations, right? Even though if you were to pick a random function and a random x value, the probability that you land in this situation is extremely high. Extremely high. In fact, technically it's 100%, which is kind of weird.
I have a question.
But yeah, go ahead.
So if you were to find like the limit of 7, you would have to like trace like 5.999, 5.9, 5 point, like, those numbers, those decimal inches.
Yeah. Let's in fact, actually, that's a good idea. Let's go ahead and do that so you can see how exactly this connects to what we were talking about like last week. Because it really does. So here I've got my Desmos up as well. So I'm going to type in the exact function that I wrote down there, x cubed minus 3x plus 5. There's the function, right? And now what we want to do is make we can do a little table of values here if we want to. Let's just call that x and f of x there. All right. And then we're going to do like, we're x approaching 2, right? So we're going to do like 2.1, 2.01, 2.001. Okay, that looks pretty good, right? And then we also want to do like 1.9, 1.99, and 1.999, stuff like that. And you can see the first three rows here, these are approaching.
Oh, wait, I have a question. So if, for example, the number on the limit is, if there is a number that you bring that's bigger than the number that's the limit, then it should be like 7.0, like 2.1, 2.01, 2.0001. But if it's a number that's smaller than the limit number, it should be like 1.9, 1.99.
That's the pattern you're seeing. That's and that is like a way. You don't have to do it this way. We could do it like 2.5, 2.05, and 2.005. Like it doesn't really matter exactly. 2.0005. It doesn't really matter exactly what the numbers are as long as they are getting closer and closer and closer to whatever the limit value is, and ideally by like orders of magnitude. So like throwing in extra zeros or putting 1.999 is, really what we're aiming for is 2.0000000 something, maybe 1, and then 1.999999999 forever, right? Those are sort of like the things we want to be getting closer to. So you might as well do versions of that with some number of zeros and some number of 9s. Yeah. As you can see, both of those, Desmos is actually literally spitting out the number 7. That is technically incorrect because it's like a rounding error. Neither of these numbers actually give the output of exactly 7. They don't, but they give an output very close to 7. That's the idea. Okay. So as you can see here, we evaluated that limit just by finding f of 2. So we didn't need to do all of that guessing, all of that work with plugging in numbers and making a table of values. The difference is that was a way to estimate the limit of a function. This is a way to directly calculate the limit of a function exactly without any approximation or estimation involved. We can be confident 100% that this is the value of this limit. Does that make sense? Okay. I don't want to spend too long on this because, like I said, most of our time and energy is going to be spent on the more challenging cases, which are coming up. So the last thing I want to say here is, the other types of functions you've studied, transcendental functions like exponential, logarithmic, and trig. exponential log and trig functions also have the same property, that they are, they're continuous everywhere, they're defined. So really what we're looking for, unless you're dealing with like a piecewise defined function, piecewise defined functions can get wacky and messy. So like none of this covers piecewise defined functions. If you have a piecewise function, then you can get all sorts of weird things, potentially. But for the most part, for these, unless it's piecewise, if it's not piecewise, then functions described, like the types of functions you've been studying in pre-calculus, college algebra, trigonometry, that sort of thing. These functions, if they're not continuous, they're going to be undefined as well. And so really that's what we're going to be looking for, is like x values where the function is undefined. And those are going to tell us where the discontinuities might be. And those are the points where we're going to be spending more of our time figuring out, how do we solve this limit? All right, so next example. Now we're going to spend time talking about those cases. Okay, so for this next example, let's look at the limit as x approaches 5 of x squared minus 25 over x squared. Just a second. Minus 4x minus 5. All right. Question. Is this function defined when x equals 5? Well, try doing f of 5. By the way, a lot of times when we're dealing with a limit, a lot of times in this class, we're going to be dealing with a limit or a derivative or something, and we're going to have like some sort of a function. And I will often just, by default, refer to that function as f of x, like that. Is that okay?
Sure. It's not defined.
It's not defined, is it?
No, denominator equals 0.
Yep. That's 25 minus 20 minus 5, that's 0. This is 25 minus 25, which is also 0, interestingly. But it's undefined, right? So no. So that means not continuous. Okay, so we cannot solve the limit by direct substitution. It's undefined. Of course we can't. All right, it's kind of obvious when you think about it like that. So this scenario is kind of special. Zero over 0 is an example. Well, I'll say that it's called indeterminate. What that means is anything could happen. It could, the limit could equal, it could be undefined. Could equal 0. It could equal 3. It could equal anything. Okay, so the word indeterminate just means it doesn't mean undefined. Undefined and indeterminate are totally different things, right? Undefined is usually the word we use when we want to say that the limit, well, undefined is usually what you use when we want to say that the function is undefined, right? In the context of limits, we don't actually usually use the word undefined. Usually what we say is the limit does not exist. I'm going to put that in parentheses next to undefined. I think what I really should have said there is like DNE, does not exist. Undefined that'll do. I think that gets the point across. But indeterminate is a totally different thing. Indeterminate is like, whoa, we don't know. There's not enough information yet to say what is going on with this limit. You've got to do some more digging. You've got to approach it in a different way. You got to take a different angle. So, so that's what we're going to do now. So what can we do with this thing? Well, one thing that we can say for sure, and this is a theorem I'm going to put down here as well. If f of x and g of x are algebraically equivalent, then their limits at, as you know, x approaches some a value are equal to one another. Okay. So if you take a function, you take the expression that describes that function and you manipulate it algebraically, if they're algebraically equivalent to each other, the limit value stays the same. Okay, so what we can do is we can take this expression and we can manipulate it algebraically and try to obtain something, try to make some progress towards something that is no longer going to be in that 0/0 format when we attempt to plug in the a value, which is 5 in this example, right? So let's see what we can do. I'm going to algebraically manipulate this expression. It needs to be still equivalent. This is why it's so important for you guys to review. This is why we were reviewing how to simplify algebraic expressions, because that is one of your like main tools for evaluating limits here. Okay, so all I'm going to do first is just factor. Let's factor the numerator. X squared minus 25 is a nice difference of squares. So you guys may remember the way this factors is like this. I'm not really planning on reviewing factoring. I figure you guys have probably been factored to death in your other classes, right? Previous classes, you do a lot of factoring. So anyway, we're going to factor the numerator. The denominator we can factor as well. Let's see. -5 times +1 is -5. And then -5 plus +1 is -4. So this is going to be x minus 5 times x plus 1. I'll zoom out again, sure. There we go. So that was what I wrote down there. So the theorem down there is saying that basically this theorem is justifying the equals sign. This theorem is justification for the fact that these two limits are equal to each other, because this is algebraically equivalent to this. Sure thing. Let's do another one. Okay, so now looking at this, is there something we can do to simplify it? You see it? You guys see?
So we can simplify the parentheses. So x minus 5 and x minus 5.
And what do we do with those?
Cancel them.
Cancel them, yeah.
Yeah, they can cancel out. That's right. We can reduce this fraction. So the x minus 5 is a common factor. It cancels out. And so now that means that this is equal to the limit as x approaches 5 of x plus 5 in the numerator over x plus 1 in the denominator. So now, having canceled out those x minus 5s, I think at this point now we should attempt again to do direct substitution. What happens when we do that?
Are we substituting in 5?
Say what?
Are we substituting 5 in?
Yeah, we substituted in 5.
So 10 over 6.
10 over 6. Or reducing slightly, I wrote 5/3. And that is the value of this limit. This function approaches 5/3 as x gets close to 5. And this is a rigorous, what's the word I want to use? It is a definitive way to show that the limit equals 5/3, right? No estimating, right? No guessing like we had with numerical and graphical approaches. This is what is called an analytical, gosh, if I can spell it, solution to a limit problem.
Wait,
There's a
it's analytical. It's not supposed to have a T over the L.
And oh yes, you're right. I spelled, yeah, you're right. I typed it here. I'll try again. Anyway, that's a vocab word for you. Analytical solution to the limit problem. And anytime you're using theorems and algebra, that's an analytical solution. So like this was an analytical solution as well over here. When we did it by direct substitution, that was analytical as well, right? Both of these are analytical. It just means that there's no estimation, there's no approximation. It's analytical means like you don't, instead of just plugging in numbers and guessing, you're actually like using sort of logical approaches, right? That say like, oh, if this, then that kind of thing. Yeah, that's kind of what analytical means in the broader sense of mathematics.
So basically, our answer 5/3. Is that what we would have gotten if we used the table and then used the 4.99? Like the number that we could see was approaching. Is that what it is?
Yep. Or... Yep. And you can try it yourself. I won't take the time to do that right now, but yeah, please do. Please try it yourself, and you will see. Yep, it does appear to be approaching 5/3. But now we can say with more confidence, I mean, the table makes you pretty dang confident. But what my point is that with an analytical solution, it's like a proof. It's a rigorous mathematical proof that the limit equals 5/3, not just like, here is a lot of good evidence that it's equal to 5/3. It's the difference. Anyway, we are going to be shifting our focus now towards doing analytical solutions to limit problems as opposed to just numerical and graphical solutions. We're not going to stop doing those. We'll still do them occasionally, but like a lot more of the focus is going to be on, for the next week or so, a couple weeks maybe even, is going to be on this analytical approach. Okay, so brace yourself for more algebra. Let's export this and get a nice fresh page, and we'll do like 2 more examples. Okay, so that page is not lost, it is saved. So I'll post it for you guys later. Here is another example. Let's do the limit as x approaches -3 of the square root of x plus 7 minus 2 all over x plus 3. So first, attempt direct substitution. Is f of x defined? That's what we want to do first, right? You could do this in your head.
It would be undefined
Why so?
because the denominator equals 0.
Okay, right, good. So what's the numerator equal to, by the way?
0.
Also 0. So like Elijah said in the chat there, this is another example of an indeterminate limit. Let's get that in the notes. All right. Okay, so now that we know that, now we want to find some sort of approach to simplifying it. Okay. We want to simplify this algebraically somehow. Right? Does anyone know a strategy for simplifying something like this? It's got a square root in it.
Multiply by the conjugate, maybe?
Ooh, yeah. Multiplying by the conjugate. So this is what I reviewed this with some of you guys for the first exercise set, right? I gave you a problem similar to this involving a square root. So what we want to do here is basically like the same strategy you use to rationalize a denominator, except we're really sort of rationalizing a numerator. So what I want to do is actually get in, hang on, I forgot let's just go back to this layer here. Okay, let's get in here. And what I want to do is I want to sort of multiply this by something. I've got to make sure that it's still equivalent, right? That's key, because if it's not an equivalent if it's not an equivalent function, then its limit isn't going to stay the same. So we can't actually change its value. All we can do is manipulate what it looks like. So what I want to multiply by is this thing called the conjugate of the numerator, which is exactly the same expression as the numerator, except this minus gets turned to a plus. Why doesn't this plus get turned to a minus? Why does that plus stay the same?
Because it's in the square root function.
Yeah, it's inside the square root. We don't want to mess around with it, do we? We only want to change the operation, which is between the two terms, one of which is a square root. Sometimes you have two terms where they're both square roots. This one, when you plug it in, it turns out to be the square root of 4, which is 2. So that's a whole number. So there's no square root there. But the point is, it's only the operation between the terms that you change. Now, the other major point here is if we're going to multiply by that exact expression in the numerator, we have to multiply by that exact expression in the denominator to maintain the value of the expression overall. So there we go. So there's that. So now we can move on to
Oh, wait. I have a question.
Oh, sure. Yeah.
What happened to the x plus 3?
It's still there.
Oh,
We're not doing anything with it. We're really, I mean, we're going to multiply it by this square root of x plus 7 plus 2. We're going to multiply it by that, but we're not like, okay, so what we're doing right now is multiplying by the conjugate of the numerator only, because that's the one that has the square root in it. You don't bother multiplying by the conjugate of the denominator because it doesn't have a square root. And so there's no need to simplify it with a conjugate. Maybe this doesn't make sense because you're not sure where this is going. And when you see where this is going, it might make sense. What happens when you multiply conjugates together?
The
It
square root.
removes the square root.
It's going to cancel the square root somehow?
Yep.
Yeah. So these are conjugates. Conjugates are always in this format, A minus B and A plus B. It doesn't matter what order they are in, because it's just the multiplied together. When you multiply conjugates together, you always get this difference of squares formula, format, whatever, that sort of thing. And so the reason we're multiplying by conjugates here is so that we can get this difference of squares, and that squaring you see there is going to cancel out the square root, which is going to make it so that our numerator no longer has a square root in it. That's why we're doing this. As you can see, we don't need to do that to x plus 3 because it doesn't have a square root. All right, so in the numerator, we're going to end up with this difference of squares. The first thing squared minus the second thing, which is 2, also squared. And in the denominator, we have x plus 3 times this thing. Now, it might be tempting to like FOIL that, but don't. Just write it like that. They're multiplied together. You do have to put parentheses around each of them, because if you miss one of those parentheses, then it's technically not written correctly. So do be sure to write things correctly with parentheses.
Are you counting x plus 3 as just one term?
One factor.
So you're not multiplying x times the square root of x plus 7.
That's right. I'm not foiling it.
Okay.
By the way, so I just, for anybody who doesn't remember this vocabulary, I just corrected the word term to factor, and the difference between terms and factors is that terms are things you add together. Factors are things you multiply together. Okay, so you'll hear me, I'm kind of pedantic about this vocabulary, but the reason is because I think it really is valuable to make a clear distinction between whether things are added together or whether things are multiplied together. And having different words in our language to refer to those things, terms versus factors, just makes it easier to distinguish between them while we're communicating. So when I say cancel common factors, the things you're canceling had better be factors. Gosh darn it. One of the most common algebraic mistakes is to cancel try to cancel things in a fraction incorrectly, and people end up canceling terms. You can't cancel terms by division. Terms can cancel when you're subtracting, but they can't cancel when you're dividing, because subtraction is the opposite of addition. Dividing is the opposite of multiplication. So that's the sort of thing. And so if you understand the difference between terms and factors and you know what that means, then it just helps to keep everything straight.
But x and 3 are both terms, but you're treating them as factors in this situation.
Yeah. Oh, there's layers. It's like Inception here, because x plus 3 is a factor in the denominator, right? So this overall is a factor, and this is a factor. But then within each factor, you have some terms. Is that what you're saying?
I guess, yeah.
Yeah.
But now you have a square root in the denominator, so.
Yeah, we're gonna have a square root in the denominator, but that's actually gonna be all right. We're running out of time here, so we got to wrap this up real quick. If you have to get going, please feel free to head out. I won't be offended. This is recorded, so you can watch the last part of it later. We'll just wrap this up and call it a day. So what happens here? The plus 7 minus 4, we can simplify, right? This is it just becomes plus 3, right? Plus 7 minus 4 is 3. So that's great, because we have that x plus 3 factor in the denominator. right? Right? So now x plus 3 is now a common factor in the numerator and denominator of this fraction. So we can cancel it out. All right, so let's get in there. Cancel those. And then what's left after canceling is 1 over this square root of x plus 7 plus 2. Now that we've canceled the x plus 3, let's try direct substitution again. 1 over the square root of negative 3 plus 7 plus 2. Negative 3 plus 7 is 4. The square root of 4 is 2. But now instead of minus 2, it's plus 2 from the conjugate operation we did. So this is 1/4. And that's the answer. That's the limit, value of the limit. So this demonstrates the strength, the power of algebraic simplification when it comes to solving the limit problem. The canceling of x plus 3 was the key moment, right? This is the key moment where we went from something that was in the format 0 over 0 to something which was no longer in that indeterminate form 0 over 0. Right? Because in a way, you can think of it like this. The reason we had 0 over 0 originally was because of this x plus 3 over x plus 3. It's because of those factors. If you cancel them, now you don't have 0 over 0 anymore. So that's, yeah, I'm glad you think this is actually pretty cool. I think it's pretty cool too. It's kind of just taking all that algebra you learned and kind of giving it a little more meaning. I'm glad this is making sense. That makes me happy, folks. Let's call it a day.
Yeah, makes sense.
I have a question.
Go ahead.
I have a problem with chapter 2 homework where it's like so basically well, I'm gonna have
This might be a good office hours question. Adam, do you have a class right after this?
nah,
Can you stick around for a few minutes?
for a few minutes. Yeah, I can.
All right, cool. Just hold your horses then. I'm just going to export this, let everybody go. Bye, folks. Have a great day. I'm going to end the recording in a second here. I'll just do that now. And then we'll basically just transition straight into office hours here.
Wait, how do I get to office hours?